Welcome to the video lecture on integration of the natural logarithm. We know from derivatives that the derivative with respect to x of ln of x is just 1 over x. So in reverse, the integral of 1 over x should give us back the ln of x. So this result right here tells us that the integral of 1 over x dx equals the ln of the absolute value of x plus c, because the antiderivative of 1 over x should be ln of x. Now I'm using absolute value here just to ensure that I'm only taking the ln of positive numbers. Okay, so that's why you'll see those in these problems. Now if we generalize this, instead of just having an x, what if we have a function of x? We'll call that u. Then if you have the integral of 1 over u with the derivative of u next to it, then that will also be the ln of the absolute value of u plus c. Sometimes you'll see this notation rewritten by pushing that du onto the top. 1 times du is du. So you'll see this written as the integral of du over u equals ln of the absolute value of u plus c. And then this is the more specific rule with just an x. Now, if you want to think of this in terms of layman's terms, remember that we know that the derivative of ln of stuff is stuff prime over stuff. So this is really the same as saying the integral of stuff prime over stuff is the ln of that stuff in the denominator plus c. So if you have a denominator down here where the derivative of that is present in the top so that it fits this pattern of stuff prime over stuff, then that will be the ln of that denominator. Okay, so we're going to use that quite a bit today. So when you see fractions, you want to look for that pattern and see if it fits stuff prime over stuff, and then you'll be able to integrate it right away. Now we're also going to talk about in this lecture some derivatives and antiderivatives of some trig functions. We know a few integrals of trig functions, like for example we know the integral of sine and we know the integral of cosine. We know the integral of secant x tan x or cosecant x cotan x, and we know the integral of secant squared x and the integral of cosecant squared x. But we haven't mentioned in that list is the integral of just a tangent, just a cotangent, just secant, or just cosecant. And that's because those end up using an ln. So let's derive what these antiderivatives are going to be, and you're going to want to memorize the results of what we come up with here. So to find the integral of tangent of x, what we're going to do is we're going to change this into its sines and cosines. So tangent is sine x over cosine x dx. Now think about our rule up here. This is a fraction, and when I see fractions, what I want to start thinking about right away is, does it fit this stuff prime over stuff rule? And this one does. This is a cosine in the bottom. So if I let that be my stuff, then the derivative of cosine is a minus sign. So I have the sign, I'm just missing my minus. And we can fix that by putting the minus inside and counterbalancing by a negative on the outside. So now this does have stuff on the bottom and stuff prime on the top. So that means the integral of this is ln of that denominator, and that negative that we counterbalanced by will still be out front. So this is a real simple way to get your answer. So if you want to be a little bit more fancy about it, if you're not comfortable with this stuff prime over stuff, there is another alternative. You could use a U-substitution. So you could think of tangent of x as sine x over cosine x dx. And if you let u be that denominator, then du, the derivative of cosine, is a minus sine x dx. And I have a sine x dx right here, but I don't have that negative. So if we divide that negative over to the other side, then that means that this numerator right here gets replaced by a minus du, and this denominator was our u. So this integral, using a U substitution, turns into negative du over u. You can pull the negative out if you like. And remember, the integral of du over u is just the ln of that denominator. So this becomes the ln of u in absolute value, plus a c. And last but not least, we want to resubstitute back in terms of x. So if I change that u to a cosine, then we get the same answer that we got before. Now, it's perfectly fine to leave your answer like this, but I want to show you that there is an alternative, and most textbooks use the alternative version of this answer. So if you think about properties of logs, remember that coefficients out front can become powers up top here. So this is the same as ln of cosine of x raised to the negative 1. What happens when you flip over cosine? Because that's what a negative 1 power does. 1 over cosine is secant. So this is ln of the secant of x plus c. And that's typically how textbooks will write it, because we have sort of this association between tangents and secants when we think about derivatives and integrals. So the integral of tan x dx is the ln of the secant of x plus c. So that's the new rule you want to remember. And we can get that by either using stuff prime over stuff, or we could have done it a little bit more long way over here using a U-substitution. It's your choice. Okay, so let's try that same process on cotangent. So I'm going to change cotangent to cosine of x over sine of x. And I'm going to do it with my shortcut because I think that saves us a lot more time. So if you think of this as your stuff, then the derivative of sine of x is cosine of x, which is exactly what I have in the numerator. So I have stuff prime over stuff, which is good news. I don't even have to fix any negatives or anything like that. That means this fits my pattern that I had up here. So the integral will be the ln of that denominator, sine x, plus c. Now it's, again, perfectly fine to leave your answer like this, but what's typically done is to change this into a negative ln of sine of x raised to the negative 1 plus c. Now why is that the same as ln of sine x plus c? Well, if you were to bring this power down, this negative 1 would cancel out that negative out front, giving you a positive. So they really are the same, but if I think of it this way instead, then this negative out front will stay put, and what does 1 over sine of x become? It becomes cosecant. So typically textbooks write it this way because we have this association between cotangents and cosecants when we think about derivatives and integrals. So the integral of cotan x is negative ln of cosecant x plus c. Okay? So that's a second rule, new rule, that you want to memorize. All right, let's try the integral of secant x. Now this one, you can flip it over if you like into a 1 over cosine, but that's not really going to get you very far. Because if we let our stuff be this cosine, I certainly do not have stuff prime on top because I just have a 1. So that's not really the route we're going to take with this problem. And actually, to do this, we're going to do something that you probably would never think to do on your own. You'd need somebody to show you to do it the first time round, because you wouldn't normally come up with this probably on your own. What we're going to do is we're going to multiply this by a fancy version of 1. I'm going to multiply by secant x plus tan x on the top and on the bottom. So we're just multiplying by 1, so we're not changing the problem at all. We're just writing it in a new form. Now when I do this, this secant x is like over a 1. So secant x times both of these is going to give me secant squared x plus secant x tan x on top. And 1 times that denominator just gives me secant x plus tan x on the bottom. I'm just going to push that dx to the side. Now notice that the derivative of secant is secant x tan x. and the derivative of tangent of x is secant squared x. So if this is my stuff, then the derivative of it is this. So derivative of tangent x is secant squared x, derivative of secant x is secant x tan x. So I have stuff prime over stuff, which means this antiderivative is going to be the ln of the absolute value of that stuff in the bottom. So secant x plus tan x inside of that ln. And then we put a plus c on the end, and there is my answer. Okay, so the integral of secant x is the ln of the absolute value of secant x plus tangent x. All right, now we're going to do the same kind of trick on the integral of cosecant. We're going to multiply it by a fancy version of 1. I'm going to multiply by cosecant x plus cotangent x on the top and on the bottom. So when I distribute this cosecant across, I will get cosecant squared x plus cosecant x cotangent x all over cosecant x plus cotangent x and that dx on the side. So if I let this be my stuff, the derivative of cosecant needs to be negative cosecant x cotangent x. So I kind of need a minus right here. And the derivative of cotangent x is negative cosecant squared x. So both of these need a minus, which means I'm missing my negative. So what I can do is multiply through by a -1, counterbalance by a negative on the outside, and now this is the correct stuff prime. Okay, so I have stuff prime over stuff, which means the integral is the ln of this stuff in the bottom, and the negative that I counterbalanced by on the outside is still there. Notice that we didn't do anything with the top in either of these problems. It just needs to be there to fit the pattern and make the rule correct. You don't actually integrate that top at all. You're just integrating that rule of stuff prime over stuff. Okay? So the integral of cosecant is negative ln of the cosecant of x plus cotangent of x in absolute value. So integration is much more difficult, I think, than taking a derivative, because there's a lot more strategy involved, and there's a lot more rules, and there's a lot of problems that are just not possible for us to integrate. So here's some guidelines for integration. First and foremost, you've got to memorize all of the integral formulas that we've already learned. All the power rules, the log rules, the exponential rules, all the 10 trigonometric rules that we've learned. All the 6 for sine, cosine, tangent, cotangent, secant, and cosecant, as well as secant tan, secant squared, and cosecant squared. Those are your 10 trigonometric rules. So you got to have all of those memorized so that if you see them in an integral, you know that you can integrate them right away. Okay, if that doesn't work, then step 2, you're going to determine whether the integrand fits one of those 12 formulas directly or can be altered by multiplying the numerator and denominator by a constant so that it will fit one of those formulas. Step 3, find an integration formula that resembles all or part of the integrand, and by trial and error find a choice of u that will make the integrand conform to one of our 12 formulas. So this is kind of like that pattern recognition or U-substitution step. So if you can't make it look exactly like one of the formulas we already know, then you try to make it fit a pattern where you have that outer function f, your inner function g, and your derivative g prime present in the integral. And if that doesn't work, then you fall back on your U-substitution. Step 4, if you can't find a substitution for u, try altering the integrand by applying a trigonometric identity, multiplying the numerator and denominator by the same quantity like we did for the secant and the cosecant integrals we just did, or by adding and subtracting the same quantity to the integrand. If that doesn't work, then you have to fall back on some kind of computer algebra system like Derive or Maple or Mathematica. remember that once you get your answer, you can always check it by differentiating your answer and making sure you get back the original problem. So let's try some examples. Now, a lot of the ones we're going to do today are going to be fractions because that's what you have to see in order for the integral to be an ln. You need to see stuff prime over stuff. And if it is in that particular form, if you recognize that pattern, then that's just going to have as its antiderivative the ln of the absolute value of that stuff in the denominator. So when I see a fraction, I immediately check to see, is it possible that it could be a stuff prime over a stuff? Or is it possible to make it turn into stuff prime over stuff? So if we look at this one, I would probably want this to be my stuff, right? Because it's in the bottom. So that means stuff prime, the derivative of this, would want to be a 6, which I don't have in the numerator. But 6 is just a constant, and constants are things that you can fix and modify and adjust. So if we put a 6 on top, then we would have the correct stuff prime. But I can't just put it there without counterbalancing, so we're going to put a 1/6 out front. And now it does fit stuff prime over stuff. So this integral is going to be the ln of that denominator, and the counterbalancing factor will stay put, and we have no bounds, so there's a plus c. So this was a really easy integral to do once you checked for stuff prime over stuff. Let's try this one. The integral of x squared over 3 minus x cubed dx. So again, it's one of these fractions. So what I would immediately check for is, if this is stuff, what would stuff prime want to be? Derivative of 3 goes to 0. Derivative of negative x cubed wants to be negative 3x squared. I have the x squared on top. I'm missing the minus 3. So if we put it in there, we'll have the right stuff prime, but I need to counterbalance by a negative 1/3. And now I have stuff prime over stuff. So this integral will be the ln of that denominator. The counterbalancing factor stays put, and then we have our plus c. So it became really easy by recognizing that pattern. Now the rest of these aren't quite so easy. Okay, so let's try this next one here. This is actually a tricky one to do and to see, but it's a pretty common one that you'll find in a lot of homeworks. And I'll give you some advice here that most of these are going to be tricky the first time you do them, but with a lot of practice and experience, you get to be a lot better at spotting what would be the best technique to use to solve the integral. So practice, practice, practice. So when I look at this, if I try to think about stuff prime over stuff right away, that's probably not going to work, right? Because all of this would be my stuff. The derivative of that's going to be a mess, and it's certainly not going to have a derivative of just a 1. So it doesn't look like it's going to fit that pattern recognition of stuff prime over stuff. So we need to think of another alternative. And usually if pattern recognition doesn't work, that's when I try my U-substitution. Now, you could let your u be this inner function. That would work, but I want to show you something else you can do on a problem like this, and that's to use some properties of logs. Notice that the ln of x squared has a power on it, and we have properties of logs that say you're allowed to bring that power down out front. So that's what I'm going to do. I'm going to pull this 2 all the way out front, and in fact, when I pull it out front, that now enables me to actually pull it all the way out of the integral. It's not really a 2, it's a 1/2 when I pull it all the way out. So I got that 2 completely out of the picture. So when I look at this now, it's a little bit simpler, but it's still not going to be stuff prime over stuff. So I still need to use my U-substitution. So what should I let my u equal? That's the tricky thing. Usually figuring out what your u should be is the hardest part. If there's no obvious inner function, which when I look at this there really isn't. I mean, you might want to think it could be this x, but letting u be x doesn't really do a whole lot for you. You want u to be something more complicated than just an x. Okay? So we want to pick a u that's going to help us make this integral become simpler. So if you can't decide what inner function it should be, then look for a u that's going to also have the correct du, or derivative, inside the integral as well. And if you know those derivative rules really well, then this will not be too difficult to see. If you let u be that ln of x, then the derivative of this becomes du on the left side, and the derivative of ln of x is 1 over x dx, which is actually really, really good news for us, because 1 over x is right here and dx is right here. So both of those combined turn into a du. What about this ln of x down here? What does that turn into? That's my u, but remember, it's in the bottom, so this is like a 1 over u. So this entire integral turned into 1 over u du, with that 1/2 still out front. Now what's the integral of 1 over u du? Well, what's the theme of today's lecture? Logarithms. So that's what this is. This is stuff prime over stuff. The derivative of u is just a 1. So this is the ln of the absolute value of u, and that 1/2 stays out front. Now this does have bounds, but these are x bounds, not u bounds. So I wouldn't want to plug in my e and my e squared at this point. I need to substitute back in terms of x first. So let's do that. This u, remember, is ln of x. So this is going to become the ln of x. And now I can use my two bounds. First, I'm going to plug in my e squared, and I'm going to leave that 1/2 way out front. Forget about it for a moment, and I'm just going to plug in my e squared and my e and subtract those two inside of these brackets. So this will be ln of the ln of e squared minus the ln of e. So I plugged in my e squared, I plugged in my e. Now we need to simplify these. Remember that ln is a base e. So if you have ln base e of e squared, these two match, so they cancel out, and that is just a 2. So this becomes 2. So we have ln of 2. And then ln of e is also base e, so these cancel out, and you're left with just 1. So ln of e is just 1. And what's the ln of 1? Well, that's just 0. So this whole thing becomes a 0. So what we're left with is just our 1/2 and our ln of 2. And there's our final answer. Okay? All right, let's try another one. Okay, this next example, another tricky one to see and to do the very first time you try it. So when I look at this, again, I see a fraction, so I want to instantly think, okay, could I make this be stuff prime over stuff? And that numerator is just a 1, and that's obviously not going to be the derivative of this whole denominator. So it doesn't obviously fit that pattern right away. So we're probably going to need to break out a U-substitution. So what should we let our u equal to make this turn into something easier, something simpler? Well, you could either let u be this x to the 2/3, or you could probably let u be this 1 plus x to the 1/3. When you have choices like that, I usually choose the u to be the more complicated expression, the one that's more involved. So to me, that's going to be this 1 plus x to the 1/3. Now, another reason why this is the right choice to make is because of what happens when you take the derivative. And you want to kind of think about that in your head a little bit before you choose your u. What would the derivative of u be if I made that choice? So let's see what our derivative is. The derivative of u is just du. The derivative of 1 plus x to the 1/3 becomes 1/3 x to the negative 2/3, and the dx goes on the side. Now if I rewrite that a little bit, this 1/3 x to the negative 2/3 becomes 1 over 3 x to the positive 2/3. 1 over x to the 2/3 is what I have right here, and there's my dx. So I have this part of it. I just don't have that 3 in the bottom. So multiply that 3 to the other side, and we get 3 du will replace the 1 over x to the 2/3 dx. So these two pieces become 3 du. What does this become? That's our u, but it's in the bottom. So it's a 1 over u, and these two became my 3 du. And these are all being multiplied together. So this entire integral, this messy integral, just turned into 1 over u times 3 du. And you can pull that 3 out. So this is just 1 over u du. And that is stuff prime over stuff, because the derivative of u is just a 1. So this is ln of the absolute value of u. Last but not least, plug in back in terms of x. So remember that u is 1 plus x to the 1/3. So this will become ln of 1 plus x to the 1/3 times that 3. There's no bounds, so we put a plus c on it, and there is my integral. So we had to choose u to be something in our denominator here, and I chose it to be the more complicated piece, and that was also good because the other piece ended up being a part of the derivative that we needed for our du. Okay, so that's always a good strategy. Choose a u so that its derivative is also present in the integral. All right, let's try the next one here. Sine of x over 1 plus cosine x dx. So here's another fraction again. So immediately what is going through my head is, could this possibly be stuff prime over stuff? So let's check. If this is my stuff, then what would stuff prime be? Well, the derivative of 1 goes to 0, and the derivative of cosine x is minus sine x. Well, that's almost exactly what I have on the top. I'm just missing the minus. So if I put that in there, then I do have the correct stuff prime, but I have to counterbalance by a negative. So this negative that we counterbalanced by stays put, and since we have stuff prime over stuff, this just becomes the ln of that stuff, or the ln of 1 plus cosine x. We have no bounds, so this is going to have a plus c. Pretty easy, right? Okay, let's try another one. The integral of secant of ln of x all over x dx. All right, another fraction. But clearly, if this is my stuff, the derivative of that wants to be a 1, and I have way more than that on the top. So this is not going to be stuff prime over stuff. So what could we do instead? Let's try a U-substitution. So what should we choose u to be? Some things to think about. Is there an inner function that would make a good choice for u? Is there a function that I could let u be so that its derivative is also present in the integral? And I have the same answer to both of those possibilities. Here is a good inner function. And if you took the derivative of that, the derivative of ln of x is 1 over x dx, and that is exactly what I have right here. This x is in the bottom, so it's like a 1 over x times a dx. So this is going to become a du, this becomes a u, and that secant just stays in front of that u. So this whole integral turned into secant u du. Okay, so not only did I choose u to be my inner function, but its derivative was also inside the integral, so I absorbed that dx and that x in the bottom into my du. So this is what we're left with. Well, what is the integral of secant u? This is one of the new ones that we did today. Let me back up here a little bit. The integral of secant of x was ln of secant x plus tan x. So the integral of secant u will be ln of secant u plus tan u. So this is one of our new rules that we just learned today. So this will be the ln of the absolute value of secant u plus tangent u plus c. And now I want to resubstitute back in terms of x. So those u's are going to get replaced with an ln of x. So this becomes the ln of the secant of ln of x plus the tangent of ln of x plus c. And there's my final answer. Okay? All right. On the next example, we're going to learn a new technique here that we haven't talked about before. First of all, I see a fraction, so again, initially I'm going to think in my head, could this be stuff prime over stuff? And that won't work, because if the denominator is x plus 1, the derivative of that wants to just be a 1, and I have more than that on top. There's no way for me to get rid of that x. So what you want to notice about this one is that it's what we call a rational function. It's a polynomial over a polynomial. What you want to notice is the degrees are the same on the top and the bottom. So when that happens, that means you can usually use long division to reduce this. So here's a new strategy. If the degree of the top is greater than or equal to the degree of the bottom, then you're going to use long division first. Okay, so everyone hates long division, but it's usually not too bad on these problems. Here's what we do. We take that numerator and we divide it by that denominator. X times 1 would give me x. 1 times 1 would give me plus 1. But when we do division, we do subtraction as well to get that remainder. So I have to subtract both the x and the 1, which means both of these become minus. So the x's cancel, and a minus 1 and another minus 1 become a minus 2. So that means x minus 1 over x plus 1 is equal to this quotient 1 plus a remainder of negative 2 on the top over this initial divisor or denominator on the bottom. So this function right here is also the same as this function right here. Now why does that help me? Well, if I want to integrate this, instead I can integrate this. And that's actually going to be easier for me to do. Let's break this up into two different integrals. The integral of just the 1 dx plus the integral of the negative 2 over x plus 1 dx. Well, the integral of 1 dx, what function has 1 as its derivative? That's just x. So the integral of 1 is just an x. For this one, I have this negative 2 on top, which isn't helping me at all. So let's pull that out, and that leaves me with a 1 over x plus 1 dx. Now this is stuff prime over stuff. So this fits that pattern, which means it is going to be an ln. So this is going to become the ln of the absolute value of that denominator. The minus 2 stays in front. The x carries down. There's no bounds. So we get our plus c, and we are done. So by using long division, we were able to break up this fraction into two pieces, both of which we knew how to integrate. So that's why long division does help us in that problem. Okay, next example. Integral of secant squared t over tangent t plus 1. So I see a fraction. The first thing I'm going to think about is, could it be stuff prime over stuff? So if this is my stuff down here, what is the derivative of tangent t, secant squared t, and the derivative of 1 goes to 0. So this is actually the right stuff prime that I need. I have exactly everything that I need. So that means this is just going to be the ln of that denominator plus a c, and we're done. Really quick and easy. Okay, let's try this one. Now this one is not a fraction, so we need to think about how we can simplify this. It's not going to be an ln, at least not initially, because we don't have a fraction at all. So when we see square root of 1 plus tan squared x dx, you might get a little bit stuck here, but what you want to remember in a problem like this is 1 plus tangent squared x. That should look vaguely familiar from trigonometry, because that is an identity. 1 plus tan squared x is secant squared x. And if we replace this whole expression with secant squared x, that's under a square root, which is good because a square root and a square cancel each other out, giving me just a secant x. And that is something I know. That is that new formula that we learned today. The integral of secant x is the ln of the absolute value of secant x plus tan x plus a c. So by using an identity here, we were able to manipulate this to turn it into something that we did have a formula for. So remember those identities. Every once in a while, they're going to be useful when you're integrating. Okay, next example. This is another fraction. Obviously, the derivative of the bottom is not going to look like the top. So initially, it doesn't look like stuff prime over stuff. So that means we're probably going to need to think of a U-substitution. But one quick thing I want you to check for, this is a rational function. The degree on the top would want to be an x squared. The degree on the bottom is an x cubed. Unfortunately, that means the degree on the top is smaller than the bottom, so we aren't able to use long division to simplify it. So that technique also doesn't work for us. So what should we use for our U-substitution? Well, there's lots of choices. You've got an x, which doesn't really do much for you. You could let it be this x minus 2, or you could let it be this inside x minus 1. I would choose it to be that denominator for a couple of different reasons. There's sort of an outer function with that cube, which makes this inner function a good candidate for u. Also, letting that u become that denominator means we're simplifying this denominator so that it's no longer going to be a quantity that's being subtracted. It's going to turn into a single term in the bottom. So that's a good thing as well. So let's go ahead and find our derivatives. Derivative of u is du. Derivative of x minus 1 is just 1 times our dx. So in this problem, du becomes dx. So let's see if we can start simplifying or substituting in. This is my u cubed. This is just du. So now I need to figure out what x and x minus 2 become in terms of u. So how do I figure out what x is in terms of u? We go to here and we solve this for x. If you add 1 to the other side, you get x equals u plus 1. So this x becomes u plus 1. And if I use parentheses here, this x becomes u plus 1, and I need to subtract 2 from that. So I've replaced all my x's on top, my x minus 1 in the bottom, and my dx became my du. So now you should only have u's in your integral. So let's simplify a little bit. Inside parentheses, u plus 1 minus 2 becomes u minus 1. And having that u be the denominator is a good thing here, because that means this denominator is now a single term, and I can actually move that up to the top to totally eliminate this quotient. We don't have a quotient rule for integrals, so we want to try to avoid having that big division bar if we can. We also don't have a product rule for integrals, and right now that's what this is, a product of 3 different things. So what I'm going to need to do next is get rid of those parentheses, get rid of this product, and try to turn this into a sum and difference of a bunch of individual terms. So let's FOIL out these two guys first. That's just a difference of squares. So that's going to be u squared minus 1. And now to get rid of these parentheses, I can just distribute that u to the negative 3 across. We add powers, so 2 plus negative 3 makes this a negative 1 minus u to the negative 3. So now I don't have any of those products anymore. I just have 2 individual terms. So this is u to the negative 1. I need to integrate that term, and then I'm going to need to integrate u to the negative 3 as well. Now those both look like power rules because they're u raised to a power. But be careful on this one, because if you use your power rule, you would add 1 to the power, so the new power would become 0, and then you're supposed to divide by that new power, and we're not allowed to divide by 0. So that's your clue that this is something special. You can't use the power rule when this is a negative 1, because this is really the same as 1 over u du. And this does not have a power rule associated with it. This is an ln, because this is stuff prime over stuff. So when that power is a negative 1, you want to remember that that's the ln of u. This one is a power rule. We can add 1 to the power, negative 2, and divide by the new power. So this becomes plus plus. And if I flip that u squared back down, this becomes 1 over 2u squared plus a c. And to finish off, remember we had x's up here, so you need to go back to your U-substitution and plug in x minus 1 for all of these u's. So this becomes ln of x minus 1 plus 1 over 2 times x minus 1 squared plus c. Okay? All right, our last example here. Find the area bounded by the function 2x squared minus 14x plus 24 all over x minus 1 and the x-axis. So this is an area problem, and that's what integrals are good for. They find us areas under curves. To graph this, you could graph this on a graphing calculator. That's perfectly okay. You can also notice that this numerator is divisible by 2, so I'm going to pull out a 2. And then what's left there factors into x minus 3 and x minus 4. So the graph of this has zeros at 3 and 4. So this is going to intersect the x-axis at 3 and 4. And it has a denominator that equals to 0 at 1. So there's actually a vertical asymptote at 1. So this graph, and you can verify this on your calculator, it looks something kind of like this. So the area bounded by this curve and the x-axis is this little area down here. That's what we're trying to find. So the integral that's going to represent that is going to be the area under this curve. So we want to integrate this curve, and we want to do that over our bounds from 3 to 4. So we want to integrate this. We see a fraction, but it's not stuff prime over stuff because that derivative of the bottom would want to be just a 1, and we have way more than that on top. So a couple of things here that you might consider doing. First of all, it is a polynomial over a polynomial, which means it's a rational function, which means that you can do a little bit of long division here to convert this into something a little bit hopefully simpler. So let's try some long division. We're going to take that numerator and we're going to divide it by that denominator. X times 2x gives me 2x squared. 2x times a minus 1 is a minus 2x, but we have to change our signs. So this becomes minus, this becomes plus. These cancel. Negative 14 plus 2 is negative 12x, and we bring down our 24, and we can keep going. X times a minus 12 gives me minus 12x. Negative 1 times minus 12 gives me a plus 12. Then I change my signs again, so this becomes plus and this becomes minus. These cancel, and 24 minus 12 is 12. So what that means for us is that 2x squared minus 14x plus 24 all over x minus 1 is the same as this quotient plus a remainder of 12 over that denominator x minus 1. So the integral of this is going to be the integral of this. And that's going to be good news for us because the integral of these three pieces is something I can handle pretty easily. I'm just going to integrate the 2x, the 12, and this fraction. I'm just going to do each one separately. And I'm doing each one from 3 to 4. So this first one is good because the integral of 2x, the 2 stays put, and then the x squared, then the x becomes x squared over 2, and these 2's would cancel. So this is just going to give me an x squared. Okay? The 12 has as its integral just 12x, right? The derivative of 12x is 12. And then this one over here, we have to do a little bit of work on it, but not much. This 12 isn't helping me at all, so I can pull that 12 out front. And when I do that, I'm left with stuff prime over stuff. So this becomes that ln. So this is going to become the ln of x minus 1 with that 12 in front. So here is what my antiderivative looks like. We did have bounds, so I'm going to go ahead and do my bounds all at once here. So I'm going to plug in 4. 4 squared is 16. 12 times 4 is 48. Plus 12 times the ln of 4 minus 1 gives me 3. Then I want to subtract from that 3 squared, which is 9. 12 times 3 is 36. Plus 12 times the ln of 2. And then you can simplify here if you like. 16 minus 48 is going to be a negative 32 plus 12 ln 3 minus 9 minus 36 is a negative 27 plus 12 ln 2. So we'll get a negative 32 plus 12 ln 3. A minus minus becomes plus 27 minus 12 ln 2. And negative 32 plus 27 is negative 5. So this would be our exact answer if you wanted to leave it like this. As a decimal, this is approximately negative 0.1344. And it should be negative because from our picture, we saw that the area that we were talking about was just a little dip below that x-axis. And any area below your x-axis is always going to be counted as negative area. Okay? All right, these integrals take a lot of practice and experience, so work hard, don't get too frustrated, and just practice, practice, practice. Good luck. That concludes our lecture on integration of the natural logarithm.